Let's talk about aromaticity. What is the origin of this Hückel rule, which is the 4n plus 2 is equal to pi electrons? That is we are going to discuss in today's video. When we can call the compound is aromatic or not, for that we need to follow these conditions. The first condition is the compound should be cyclic. The second condition, there should be a conjugate system. What is a conjugate system? It's a one sigma bond and then pi bond, sigma bond, pi bond. So that conjugation is going to provide a continuous overlapping of p orbitals. So if the overlapping is there, that delocalization can take place. Third condition is the compound should be a planar. Yes, if the compound is planar, that means what? That is again the overlapping is continuous. The delocalization can take place. If the compound is non-planar, there is a twisting and bending and all that, so that the delocalization of electrons and that density is not going to take place, so the overlapping will be poor, so compound cannot undergo aromatic feature. And the fourth one, which is we are going to discuss in today's video, that is a Hückel rule, and that's a 4n plus 2 is equal to pi electrons. We'll see what is the origin of this Hückel rule. Where did this 2 came from, and what this rule is going to have a relationship with all this? Let's see. First of all, let's see an example of benzene to understand this. This is benzene. There are 6 sp2 carbons are there and 6 p orbital is there. 6 atomic p orbital is there. And now this p orbital are going to produce overlap for delocalization for that pi system. So this p orbital can have overlap in two ways, in two manners. You can see that these phases of this orbital, these are not charges, these are the phases. This is plus phase, negative phase, plus phase, negative phase, negative phase, plus phase. So these are the phases of that waves, we can say that, of that orbital. Now if we see that overlapping again, you can see that this positive phases are going to overlap. That same phase overlap called constructive overlap. It's called a constructive overlap. That's called a bonding interaction. It favors stability. And on the other hand, if the opposite phases are going to overlap, which I have mentioned in red color, you can see that this red, this is what it's opposite overlapping, that is a destructive overlapping, and that destructive overlapping called anti-bonding overlapping, anti-bonding interaction, and that anti-bonding interaction are going to cause the instability. So if we have 6 p orbitals, that means what? As per the mathematical, we can say that equal amount of orbital are going to either overlap from same phase or either overlap from opposite phase. So if we have 6 orbital, 3 of them can go under constructive overlapping and 3 of them can go under destructive overlapping. Now let's see the origin of this 4n plus 2 is equal to pi electrons. What is this 4? Where did this 4 came from, and where did this 2 came from, and what is this n? Let's see. So if we see the structure of benzene, there are 6 pi electrons present. How many pi electrons are there? 6 pi electrons. So 4n plus 2 is equal to 6 pi electrons. How those electrons are going to filled in this bonding and anti-bonding orbitals? For the stability, what thing is required? For the stability, the bonding interaction, the constructive interaction is required, not an anti-bonding. Yes, anti-bonding overlap can take place, but those anti-bonding overlap should not have any electrons. That is a condition. So for that, we just need to fill these 6 pi electrons from benzene to the molecular orbitals. And for that, now let's see the molecular orbital energy diagram. You can see that diagram, that is the lowest energy and that is the highest energy. lowest energy is from the bonding interaction. That if there is a constructive overlapping, that means there is a lowest energy. If there is a destructive overlapping antibonding interaction, that's a highest energy. So as per the molecular orbital theory, the first orbital is having a maximum lowest energy, and that is our pi 1 orbital, and the upcoming two, one and after the upcoming two, will be a degenerate pi orbital. What is a degenerate? Degenerate means a similar energy, same energy in that upcoming two orbitals. We can see that pi 2 and pi 3, these are from the same energy pattern is there. And again upcoming two orbitals are again having a same energy, degenerate energy, but now at this time this belongs to antibonding, because all the possibilities are there. And that six, the last one, is now belongs to highest energy, that is called an anti-bonding pi 6 star. The star means what? That anti-bondings. So these three anti-bonding and three bonding orbitals are there. And how many electrons we have? 6 electrons we have. Now we just need to fill those 6 electrons into this energy diagram of molecular orbitals as per the Aufbau rule. So as per that rule, one orbital can hold 2 electrons. It can have 2 electrons. So that pi 1, that lowest energy orbital, will have 2 electrons. Yes, from those 6 electrons, 2 electrons filled in the lowest energy. And how many electrons now left? 4 electrons left. And now those 4 electrons are going to the pi 2 and pi 3. So 2 electrons are going with pi 2, and that last 2 electrons are going with the pi 3. All the 6 electrons are filled in the bonding orbital, lowest energy orbitals. Not any electrons is filled in this antibonding orbitals, antibonding highest energy orbitals. That means what? In the structure of benzene, all the electrons are going to the constructive overlapping, stabilized overlapping. If antibonding orbitals having electrons, that leads to formation of instability, unstabilization. And if the unstabilization is there, the compound is, we can say, it's unstable, it's not belongs to aromaticity. That's why if antibonding orbital is going to have electron, that compound is not going to call uh, aromatic compound. And in our case, in our benzene's case, we can see that all the electrons are filled in the bonding orbitals, so that is an aromatic. Now what this thing is have is having relationship with this 4n plus 2 is equal to pi. Let's see why this 4. Why this 4? If the 4 belongs to what? You can see that this degenerate, this same two orbitals in this case, in each case, are having 4 electrons. They can have how many electrons? 4 electrons. And because of this, degenerate orbitals can fill these 4 electrons, the upcoming antibonding orbital remain empty, and that's why it's being aromatic. Understand? So these four electrons are filled into this degenerate upcoming two orbitals. It leads to make the compound aromatic, and because of that, that 4 number is crucial. So that 4 is there. And now why this 2 is there? The 2 is there because the lowest energy is having how many electrons? 2 electrons. So what is the pattern? You can see that one, this orbital can have 2 electrons, then upcoming 2 can have 4 electrons. And if this pattern continues, never antibonding orbital will have electron. So in this pattern, which pattern? 2 6, then 10, 14, 18. This pattern continues, never that anti-bonding orbital will fill. And so this pattern is so much important for and stability, for that aromaticity, for to call the compound is aromatic. So 2, 6, 10, 14, 18. What's the pattern again? It's a 2, then plus 4 plus 4, so 4 is every time is going to add it, so that's why this 4 derived. And this 2 means what? That is what the first is always having 2 electrons, and that is that orbital can have 2 electrons. So this pattern, which pattern? 2 and then 6, 10, 14, 18 is going on and on and on. So this is what a Hückel rule is all about. Understand? When this pattern is continuously going, that anti-bonding orbital is not going to fill, and so this compound is called aromatic, because the anti-bonding orbital is will remain empty. What is going to happen? Instability is not going to be a part of that compound. If there are a 10 pi electron present in the compound, so that means 10 orbitals will form as well, phi bonding and phi anti-bonding. So now those 10 electrons are going to fill in what? In the bonding. How? 2 in lowest, then 4 in upcoming 2, and then 4 in upcoming 2. Thus in that 10 pi electron containing compound, that anti-bonding orbital will remain empty, and because of that the compound will go under aromatic feature. Hence what? This pattern is very much crucial. So 2, 6, 10, 14, 18 is going on and on for aromaticity. Now what is this n? N is a mathematical, we can just prove that this pattern is going on, and for that we just use this n. So this n should be what? Integer. If the n is being 0, 1, 2, 3, 4, 5, 6, 7, this integer, that means what? This pattern is going on. But if this n will become non-integer, we can say 0.5 and 1.5 and all that, that means what? This pattern, this fashion is going to break. So what? That means now this antibonding orbital is also going to fill, and once the antibonding orbital is going to fill, that is going to cause instability. The stability is disturbed, it's diminished. That's why the number n number should not be non-integer. So let's see an example. For an benzene, it's 4n plus 2. So 4n plus 2 is equal to 6 pi electrons. So now what is n? It's a n, 4n is equal to 4, and n is equal to 4 by 4. Yes, n is equal to 1. So this is what the aromatic compound. That's why we are going to obey this 4n plus 2 is equal to pi electrons. This is what the reason.